Welcome to another episode of Reservoir Seismology, a series of videos presented by Sterling Seismic Services on modern seismic methods designed to improve production from reservoirs. Feel free to browse our library of videos on the Sterling Seismic website under Tech Talks. This episode is on multivariate seismic analysis to identify better drilling targets. I'm your host, Brian Fuller, VP of Reservoir Geoscience at Sterling Seismic and Reservoir Services. As a quick outline, we'll first talk about the motivation for doing multivariate analysis of seismic data. Then we'll talk about some ways to apply it, application concepts for seismic data. And then we'll talk about MVA results and deliverables. A common scenario in field development and even exploration in some cases provides motivation for multivariate analysis. In this map view sketch, wells A and C are producers from a given horizon, but well B is a dry hole or at best a poor producer. If we can eliminate well completion problems as a cause of well B being a poor producer, then stratigraphic properties of well B might be dissimilar to those of productive wells. This situation occurs with both vertical and horizontal wells. So everything we say here about multivariate seismic analysis applies to horizontal as well as vertical wells. Two economically important questions are, where can further productive development wells be drilled? And two, is well B a local anomaly or is this non-productive rock more widespread? Drilling to find the answers to these questions can drive finding costs higher and reduce or even eliminate profitability of a field. Very often, seismic data in a field will show variations between the wells, but those variations are small, and it may not be possible, at least based strictly on the visible trace variations, to correctly interpret why one well is productive and another is not. There are many seismic attributes other than the most commonly displayed attribute of amplitude, and all these attributes provide information about a reservoir. For our multivariate analysis, we can use any number of attributes for analysis, and they most commonly are related to amplitude, frequency, AVO attributes, and structural attributes such as dip, azimuth, and curvature. Our multivariate statistics workflow looks like this, in which we start with the training phase over on the left-hand side of the page. We first compute the windowed attributes at the producing horizon for all data traces in the data set. So that's where we extract our amplitude, frequency, AVO, etc. attributes for each data trace. Then we extract the attributes at the location of training wells, either dry holes or producers, or even some other data traces for which we have some other information. And then we can determine the attributes that uniquely separate the training data sets from one another. Now we move on to the classification phase. We take that list of attributes that uniquely identify each well from each other, and all the data traces, we combine those and we classify all the data traces as being most like specific training wells, for example, well A, well B, etc. And we also compute a confidence measurement that the classified data trace is in fact like well A or well B, how much it is like well A and well B. And in fact, the confidence measurement is as important as the classification. So those two things need to be used together. And then we output the classification values and the confidence values as ASCII surfaces, XYZ values, and we can output them as a seg-Y volume. This is a sketch of what a classification map can look like. Multivariate analysis might classify the data traces as the green area being most like the data traces near well C, data traces in the blue area being most like data traces around well A, and the data traces in the tan area are most like the data traces at the dry hole or well B. Now, according to this plot, the stratigraphy similar to the dry hole in well B is restricted to the tan area, and the blue and green areas have a higher likelihood of being like either the productive wells A or C, respectively. The classification plot is accompanied by an equally important confidence plot that shows the probability of membership in the group to which a data trace was assigned. The confidence maps also commonly show stratigraphic packages that are unlike any of the training wells by showing a zone of low confidence. In other words, a low confidence zone is like none of the training wells, and so it shows up as a low confidence zone. In some places, these zones are channels, as sketched here. Sometimes channels appear really in extraordinary detail, showing overbanks, bars, and multiple episodes of stream channels overlaying each other. Used properly, if you're looking for channels as an exploration target, this technology is really quite amazing at extracting channel locations from a data set. The classification and confidence maps are output so they can be imported into an interpretation system and then combined with other information such as structural contours, say in the picture seen above. The format of these surfaces can either be XYZ value surfaces in ASCII or binary format. Alternatively, the surfaces can be exported to a seg-Y volume in which the classification and confidence values can be stored as flat surfaces at predefined time or depth horizons in the volume. Geographics users find this format particularly useful to import the whole volume and then look, for example, at time 0 for the classification horizon, take the values of the classification horizon and overlay them, for example, with contours and well locations. As a quick review of what we've just covered, any number of numerical attributes can be included in our software. Attributes are typically related to frequency, amplitude, AVO, structural attributes such as dip, azimuth, curvature, etc. The training data are normally at wells where we know something about the tops and the stratigraphy, and those are input to an attribute analysis that separates the attributes from one another and gives us the best separation between the training data sets. And then all data traces are classified as to which training traces they are most like, which is then output along with a confidence measurement. And then the results are output to a format that's convenient for importation to interpretation systems. Thank you for joining us today. If you have questions about this technology or anything else we do at Sterling Seismic and Reservoir Services, please feel free to browse our website at sterlingseismic.com. Call us at our office in the United States at phone 303-347-9011 or contact me, Brian Fuller, via email bfuller@sterlingseismic.com.